In this video I want to talk about comparators. So if you remember when we were talking about the basic definition of the XOR gate, so let's just say we have A and B as the two inputs of an XOR gate, and we have Y, and let's just say this is the XOR gate, so A, B, and the output is basically Y. So when we created the function, we said that for 4 possible combinations that we can have for the inputs and outputs, whenever only one of the inputs was true, the output was 1, and on all other cases the output was 0. This was for the definition of the XOR gate. But what about for the XNOR gate? So the XNOR is basically the inverse of the output of XOR. So I can just say for the XNOR it is going to be Y bar. Or let me just define it as a different function. So let's just say we call it Z. So 0, 0, 0, 1, 1, 0, and then 1, 1. And here we have A and B as the 2 bits of inputs, and Z is the output of the XNOR gate. So for this, whenever A and B were both 0, the output was 1. Also, whenever both of them were 1, the output was 1. And for the other two combinations, the output was 0. So as you can see here, the output of the XNOR gate is actually, for the two inputs, is actually checking whether the two inputs are equal or not. Because when both of them are the same, the output is 1. When they are different, the output is going to be 0. So now let's say we have two multi-bit numbers, A and B, and we want to check whether these two are equal or not. So the general symbol for this circuit, for a comparator circuit, is like this. We have A as input, B as input, and then the output is 1 bit that either shows whether the two are equal or not equal. So what we can do basically is that we can compare the individual bits of A and B with each other and see whether they are equal or not. So assuming that A and B are having both 4 bits, of course this can work for any number of bits as long as the number of bits between A and B are equal. So what we can do is that we can compare the 4th bit from A and the 4th bit from B, the 3rd bit from A and the 3rd bit from B, the 2nd bit from A, the 2nd bit from B, and then the 1st bit from A and the 1st bit from B. So if any of these things is not true, the final answer, which is calculated as the result of ANDing the output of these individual XNORs, is going to be 0. But when all of them are true, the output is going to be 1. So let's just take a look at one example. So let's just assume A is 1, 0, 1, 1, and let's just say B equals 0, 1, 1, 1. So for this example, the value for A is 1, the 4th bit, then we have 0, then we have 1, and then 1. And for B, it is going to be 0, 1, and then 1, 1. So now, XNOR of 1 and 0, it is going to be 0. XNOR of 0 and 1, it is going to be 0 again. XNOR of 1 and 1, it is 1. And XNOR of 1 and 1, it is going to be 1. But now to calculate the equal signal, we basically AND these 4 values together. So 0, 0, 1, 1, all being ANDed together, the output is going to be 0. So that basically tells us that these two numbers are not equal. But now let's just tried with a different value of b. So let's just this time put a value of b exactly the same as the value of a. So here we have 1, 0, and then 1, 1. So now when we calculate the XNOR of 1 and 1, the output is 1. XNOR of 0 and 0, again it is 1. Because this is basically the function, the output of the XNOR when both of them are 0. Then again, being A as 1 and B is also 1, that bit, the XNOR is going to be 1, and finally it is the same for the first bits too. So this is again 1. So now, since you have 4 1s as the output of the initial state, the result of this AND gate is going to be 1. So basically, this says that this number and this one are equal. So, but what about if we want to know whether a value is smaller than other one or not? Using this circuit, we cannot achieve that. For that purpose, we can use the subtractor block that we have seen before. So let's just take a look at a few examples in with decimal numbers so we understand what's happening. So let's say we have A as 10 and we have B as 8. So if we calculate A minus B, we basically have 10 minus 8, that is equal to. But now for the second example, let's just have A as 12 and B as 15. So in this case, when you calculate A minus B, what you basically get is negative 3. So as you can see, when A is greater than B, when you do the subtraction, you get a positive value. But when A is smaller than B, when you do the subtraction, the value that you get is negative. So this is one way of checking whether a value is smaller than another value or not. So as long as A is greater than or equal to B, the result is going to be positive. We consider 0 to be positive too, because when we represent 0 as a binary number, the sign bit is going to be 0 or positive. On the other hand, when A is smaller than B, when you do the subtraction, what we have is a negative value. So that is basically what we want to achieve using the subtractor circuit. If we have A and B as the inputs, and this one is basically calculating A minus B. By looking at the sign bit or the most significant bit in the output, we can determine whether A is smaller than B or it is larger or equal to B. So what is happening here is that we have A and B as the input. We calculate A minus B, and the output has the same number of bits as either A or B. But we only care about the sign bit or the most significant bit. So that is basically what we are doing. We extracting the most significant bit, or we only look at the most significant bit. So this bit is going to be 1 when A minus B, or when A is smaller than B. If you remember from before, for binary numbers, if we had a negative number, the sign bit would be 1. Especially for 2's complement, you remember that the sign bit not only had a negative sign associated with it, but also it had a weight too. So since all of the calculations that we do is going to be on 2's complement format, whenever this sign bit is 1, that means that the result is a negative value. So A minus B producing a negative value, that shows that A is smaller than B. And if this sign bit is 0, that shows that A is either equal to B or it is larger than B.